Now you should be receiving a new one. Sound check, 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 check. Sound check, check. Sound check, check, sound check, check. Sound check, sound check, check. Sound check, 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 sound check. Sound check, 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 sound check, sound check. 1, 2, 2, sound check, check. Are you getting anything from me? 1, 2, and 2. Thumbs up. If you're getting anything, yes? Yay! Okie dokie. Perfection.
One, two.
think maybe it's this guy over here?
I don't, maybe we could get Michael over.
And ask him? Okay.
Yeah, or Sarah. Yeah.
Maybe Shara then.
Yeah.
Is it at the beginning of this slideshow?
No, that's all this slideshow here.
It's not, it's in the folder.
But it's not in the slideshow itself. So we should start with it. You know, come over here with
We want to start with the video. Oh, I'm sorry. I thought it was attached to the...
It's okay. It's tweaking. Okay. So I just want to make sure that I understood right. Alright. Is this the video that we're talking about? Let's see.
Yeah,
That's the video, right?
keep going. Let me just see.
Let me just
click somewhere.
Yeah, let me just mute it first.
Yeah.
Is that the video?
That's it. That's it,
perfect.
right?
Okay. All right.
Sure.
Yeah, I mean, yeah, we don't mind the...
Yeah.
That all gets
But
edited out.
we do the video, and then here it comes.
No. Harry's going to go first.
And then video.
And then the video.
You got it.
And then Douglas. Yep. And Douglas, when it comes to Q&A,
Yes.
I think I'm going to have... Sure. And I'll run around. I have a feeling it's going to be relatively short.
Yeah.
We have so many
Oh,
speakers.
yeah. Yeah, no worries.
Okay.
All cameras are set to camera audio. Sounds good. That does matter. Let's
Good evening, good evening. Hi everybody, I'm Harry Helling, the Executive Director here at Birch Aquarium. Would like to welcome you all this evening. I'm so excited, it's going to be another amazing talk. Those of you who are regulars here know that we had a little system that we've been working on for more than 20 years where we had sort of a two-part introduction, and I had this sort of long drawn-out way of introducing our speakers. Well, we've improved that. And I'm going to talk a little bit about that tonight, but want to welcome back for the second time Michael Taylor, who's with us from NWB Imaging, a 3-time Emmy award-winning producer who's helping us fix that issue. And you're going to see a produced piece that now will introduce our speakers in a way that honors them much better than a verbal read introduction. So stay tuned for that. Tonight, also a change. We are experimenting with and piloting live streaming. These talks have always been viewed far and wide across the world, globally really, But they're recorded talks and they're archived and people have a different way of finding them. We're experimenting with live streaming these so that we can invite audiences eventually from all over the world to join us. You guys will be the live audience and enjoy these pre-talks. The folks live streaming may not get the benefit of this banter that you're all enjoying now. Also, some difference in lighting. I see we've got some brighter lights and darker audiences, so I'm getting used to that. And a few different camera angles. You all are being filmed right now, which is new, so you're part of whatever is being produced. So just remember that when you're responding. And I think that's all on that. A few other quick announcements before we get started. All of you, if you turn around and look, you'll see there's a wall right there behind you. That formerly was the entrance into Hall of Fishes. So after 32 years, we've decided we needed to renovate our Hall of Fishes, and we are deep, deep in that renovation project. We're about a month and some change into that. It's unrecognizable now. All the flooring is gone, the ceilings are gone, most of the tanks are emptied. It's a very, very necessary upgrade in all of our systems. Many of our tanks are going to get bigger. We're trying to create a much healthier and better system for the animals that we're charged with keeping healthy. As well, we're improving the guest experience. So please be patient with us. All of you who come here will be in this condition for almost 6 more months. And so we're asking all of our members and friends to help support us and be patient with us. This is all very necessary. We promise you're going to love it when we reopen it. And we've opened up a series of brand new guest experiences that we hope you will enjoy even more. So I'm not sure if any of you came early enough to enjoy the new Getty-funded Embodied Pacific, but a new 2,500 square foot exhibit partnering 10 of our Scripps scientists with local artists. It's an amazing exhibition. We opened it on October 4th, the day that we closed off our Hall of Fishes. We opened that. As well, we opened up a new exhibit, another art science partnership with the Academy of Sciences in San Francisco, and that's Riveropolis. So if you've got especially small kids, you're going to love that new exhibit. And then, really sort of interesting, for all these years, you've been seeing all of our warm water animals in our the tropical section of our Hall of Fishes. You've been watching them sort of all coiffed and beautiful, sort of from this side of the tank. Well, we thought we would give you a little different sense of what it's like to take care of those animals. And so we moved them into our classrooms where we could keep them safe while we're doing the construction. And we created a behind-the-scenes experience, which we're lovingly called Coral Classroom. So if you'd like to see our animals in a completely different way, see how we take care of them, how we manage their well-being during this construction, come join us and take a look at Coral Classroom, Riveropolis, Embodied Pacific, or starting in another week or so, our new Animal Ambassadors program where we're bringing animals out to you. So there you are. There's a quick introduction to what's happening at Birch. Okay, next, a POS talk is Noelle Boland from Scripps alum, currently the NOAA lead on the Cal Coffee program, which, if you're not familiar, is an incredibly important long-term observational record of fishing and climate change impacts on the ecosystems of the California current. So please join us next month, November 11th. And then tonight. Oh, I'm sorry, November 18th. Thank you. Right, we moved it. Okay, November 18th, thank you. And so tonight, very quickly, I want to introduce 2 speakers that you'll hear more about in the video. But tonight's talk is really about celebrating the 60th anniversary of a very important part of Scripps Institution of Oceanography called the Hydraulics Lab, lovingly called the HLab. I myself worked in it for 1 year as just a low-level sort of grunt designing and engineering a buoy. Tonight, you're going to meet Doug Alden, who's the lead engineer for the Center for Western Weather and Water Extremes, CW3E, and also you'll meet on the video, and then you'll meet in person Dr. Grant Deane, Senior Research Scientist here at Scripps, Research Oceanographer in charge of SOARS, which is the Scripps Ocean Atmosphere Research Simulator. With that, introducing Doug Alden.
Graham Perspectives on Ocean Science lecture series features engaging presentations. The Jeffrey B. Graham Perspectives on Ocean Science lecture series features engaging presentations on research conducted worldwide by scientists from Scripps Institution of Oceanography at UC San Diego. Scientists at Scripps are exploring Earth's mysteries in hundreds of research projects. Scientists at Scripps are exploring Earth's mysteries in hundreds of research projects underway on every continent. Learn about science at Scripps and join researchers on their paths to discovery.
This is the 60th anniversary of the Hydraulics Laboratory. It was built in 1964. This is the 60th anniversary of the Hydraulics Laboratory. It was built in 1964. The idea was put forward by Roger Revelle, and Doug Inman went out and got the funding for it. I think SOARS is moving us in the direction, building upon that long history. My name is Douglas Alden. I am currently the lead engineer for the Center for Western Weather and Water Extremes here at Scripps from a very early age. I mean, I took a class at Scripps when I was 10 or 11 in marine biology. I began my journey here 37 years ago in the building behind me, the Hydraulics Laboratory, when I started working as an undergraduate mechanical engineering student. For me, working in the Hydraulics Laboratory and everything I learned is standing on the shoulders of giants. I mean, all the different researchers, engineers, technicians, I mean, they're the culmination of who I am, the knowledge that I have. It comes from them. I think I would be the engineer I am today. The laboratory over the years has changed as the science has changed. There used to be, in addition to the glass channel, which is the oldest facility in the building and it still exists, there used to be a wind wave channel, which SOARS replaced. There was a deep tank. There was a stratified flow channel, granularized fluids mechanics basin, a pressure temperature testing facility, some pressure testing vessels. And all of those contributed to a long history of the laboratory and the science that was being done. And as we move forward, we don't know what's going to come. SOARS is emblematic of that. During my talk, I hope to share some anecdotes of what it's like to be an engineer at Scripps, but also working in the hydraulics lab, what it was like to work as a student in the hydraulics laboratory. I'm looking forward to present at the Jeffrey B. Graham Perspectives on Ocean Science lecture.
We have to understand the planet that we live on better. The ocean boundary is a critical boundary. SOARS simulates that ocean boundary from the poles to the equator, from the past through to the future, with the winds, the waves, and the biology that go into this complex part of our planet. My name is Deane, and I'm a research oceanographer at Scripps Institution of Oceanography, UC San Diego. I was born in Tiawamutu, which is quite close to Hamilton, south of Auckland, on the North Island of New Zealand. I was always drawn to the ocean as a child. We lived about 10 miles from the west coast of New Zealand on the North Island. If you listened carefully, you could hear the surf crashing on the beach. We worked hard on the farm. When I was younger, I always wanted to be a marine biologist. I applied to Oxford, they said no. I applied to Cambridge, they said no. I applied to Oxford again, and they said yes. In 1986, I packed my bags, I got on a plane, I left New Zealand, I flew to England and spent the next 3 years at Oxford. What do I like to do when I'm not working on SOARS? I love reading, I'm an avid movie watcher, so I train Brazilian Jiu-Jitsu. I think it fits well with my philosophy of life and conflict resolution. Through Brazilian Jiu-Jitsu, you can control the situation without hurting them. You can look after yourself and them at the same time. I approach my science in the same way. We're in conflict with the planet, or at least one can see it that way. Our need to protect and defend the planet, and our need to consume and use energy is often two needs that are in conflict. What can we do about that? Is understand it better. If we understand how the planet is responding to our choices and our activities, we can learn to live well with it. I believe that. SOARS is an effort to understand the planet, to continue to protect and defend the planet as we continue to use energy to continue to live our lives. Scientists and engineers have been building wave channels and tunnels since the 1800s. But there is no other channel that can simulate winds and waves with the temperature control, with the gas composition and the atmosphere control, with the biology that turns out to be a critical part of this boundary. SOARS is the only simulator on the planet that can do all of these things at the same time. Hello, I'm Dr. Grant Deane. Welcome to the Jeffrey B. Graham Perspectives on Ocean Science lecture.
Well, good evening, everyone. With that kind of an introduction, it's really special to be here. And as I noted, I've had a long association with the hydraulics laboratory and had an office and a work studio in the building up until a few years ago. The hydraulics lab, or is more commonly known as the HLab or HLab, recently celebrated its 60th birthday. My presentation serves as a preamble to the keynote talk that follows with a focus on what has it been like for me to essentially grow up professionally from an undergraduate student and become an engineer in the space. Keep in mind that this is the lab is seen through my own lens, and it just begins to scratch the surface of what goes on in the lab and the long history of the lab. So with that, why don't we jump right in? So a little history is warranted to set the stage. For that, I did some digging through the Scripps archives. It happened to be an opportune time to be doing some research as the library was just finishing up on cataloging Doug Inman's papers. I have to say that if you have an interest in the long history of Scripps and the associated scientific pathways of discovery, it's easy to get lost in the archives. Luckily for me, the reference librarians had set aside a few select boxes with pertinent information, as I probably would have gotten lost in the archives. While the idea of the hydraulics lab was something that Roger Revelle had been thinking about, it was Inman that was instrumental in getting the funding for a facility that would bring ocean and estuarine processes into the laboratory, enabling rigorous experimentation. Pardon. The HydroLab is a 15,000 square foot all wooden building with a distinctive wave-shaped roof line that was designed by Frank L. Hope and Associates. For those unfamiliar with where it is on campus, it's just north of the pedestrian bridge that crosses La Jolla Shores Drive on the west side of La Jolla Shores. It is tucked down below the hill, but the roof line in some way mirrors the activities inside. Interestingly, because of its large size, in its earliest years, it was a hub for Scripps social events, all in the same confines that housed facilities to study advanced fluid mechanics. And one of the people that I used to work in the lab with, Charlie Coffin, talked about some big party where a band was set up on the mezzanine and there was dancing down below. So there's a strong connection between scientific discovery and engineering. As an engineer, we are tasked with coalescing a researcher's idea into a system from which the necessary data can be acquired to support or refute a hypothesis. And is often the case, it needs to be ready tomorrow, cost very little because the budget is limited, and be able to collect data while making your morning coffee. all kidding aside, the stronger the partnership, the better the outcome. The HydroLab is emblematic of this partnership. So starting as an undergraduate student and then a newly minted engineer, how do you develop the jack of all trades skills required to support research in the lab and in the field? Well, you surround yourself with some great mentors. During my time in the lab, I was part of a team that kept the numerous experimental and testing facilities operational, assisted researchers with experimental setups and facility operation, designed novel instrumentation, and supported field work all over the world. From their knowledge and through their guidance, I turned the theoretical I gained from my education at UC San Diego into the practical. During my time in the lab, the facilities available to researchers were numerous. The HydroLab staff had the formidable task of keeping all these systems operational, from the freshwater and saltwater systems, the plumbing, wave and wind generation, electrical controls, data acquisition computers, sensors, modifications, and attendant maintenance. With many of this, I played a small part, essentially a small cog in a big machine that kept the HydroLab humming. I used this last image for a good reason. It is in it, we are testing a raft that I helped develop along with Chip Cox, John Lyons, and Jin Zhang to study whether oil spread on the surface of the water would dampen wave energy. The raft had several wind sensors, a GPS to give it position, and an inertial measurement unit that we could use to remove the motion of the raft from the wave from the data collected about the winds. And it was great to be working with Chip. It turned out to be his last research project. We had a long history of collaboration, and I feel fortunate to have been a small part of his research endeavors. As they say, standing on the shoulders of giants. Most of my time in the lab was spent supporting field research, designing and engineering mechanical systems and associated data acquisition equipment and sensors. Through it, I expanded my skill set from mechanical engineering through to electrical engineering, computer science, and data science. There were so many opportunities to learn, and not just engineering, but science about the science that we were helping move forward. I would not be who I am today without the exposure it had to such a diversity of projects and a diversity of people working in the earth sciences. The field research activities at the HydroLab could often make it a messy, seemingly disorganized space, but under the chaos, there was a dedicated team at work that supported the scientific facilities. Dedicated team at work supported the scientific facilities for researchers and then used those same facilities and the other unique capabilities of the HydroLab to support field campaigns the world over. For dozens of scientists on and off campus, including the Center for Coastal Studies, the Integrative Oceanography Division, Marine Life Research Group, Marine Physical Laboratory, the Institute for Geophysics and Planetary Physics, the Geosciences Research Division, the Climate, Atmospheric Sciences, and Physical Oceanography, Division of Biology, even the Stewart Collection, UC Santa Barbara, UC Merced, University of Delaware, Oregon State, the US Geological Survey, and on and so forth. With so much great science going on in the HydroLab and at Scripps in general, it provided a great opportunity to learn and grow as an engineer. So going back to when the lab started, Doug Inman and the other researchers could not have imagined the science that would come out over the decades in the hydraulics laboratory as they embarked on those initial studies of waves and coastal processes. Skilled technical staff and the adaptability of the facilities have enabled a diverse set of experiments to be conducted, Modifications to the glass-walled channel, also called the glass channel, enabled the Center for Aerosol Impacts on Climate and the Environment with Kim Prather and her colleagues to start investigating the complex ocean-atmosphere system. And now, the Scripps Ocean Atmosphere Research Simulator will lead us into the future, providing significant capabilities to answer complex questions that are challenging to us today and future lines of scientific inquiry yet to come. And I want to thank you for your attention tonight. I hope you've learned something about the hydraulics lab, and I'm open to answer any questions you might have, and I'll do my best to answer. Okay, great. All right, thank you.
We have to swap out the talks, and I'm not going to do it.
That's this guy, right?
Mm-hmm. Perfect. Thank you.
You're welcome.
My name is Deane. I'm the principal investigator for this machine that we have built in the hydraulics laboratory. So I'm going to tell you a little bit about that. And then I'm going to hand the podium over to two of our next generation scientists who are going to be telling you about the research that they're doing in the machine. I'd like to acknowledge some people. SOARS was a monumental undertaking. It was a $4 million machine that cost $7 million that was supposed to be built in 2 years that took 4. There was a gang of 5 of us, Farouk Azam, a globally known marine microbiologist, myself, Ken Malville, a physical oceanographer who's no longer with us, Professor Kimberly Prather, and celebrated atmospheric chemist, and Dr. Dale Stokes, another, as he was reminding me today, known by ChatGPT for his work at the Institute of Oceanography. I myself am not, but that's fine. So you'll notice a theme here. We have a microbiologist, physical oceanographers, an atmospheric chemist. The ocean doesn't know about scientific disciplines. The ocean just does what the ocean does. We, as scientists, tend to break ourselves up into disciplines. But if we want to understand this boundary, where the air meets the water, that covers 71% of our planet. When you look from space, what you're most likely to see are clouds in the water, not land. This boundary that has a profound impact on weather and climate, that impacts our future, and now, for the first time in human history, the future of the ocean depends on us also. We are coupled, we are intertwined, an interdependent fate. We need to understand it, and to understand it, we need to rebuild it as best we can with the biology and the chemistry and the atmospheric controls and the waterside controls. And such a facility did not exist on the planet until we built SOARS, which is why we did it. We really need to understand the boundary. We built SOARS to do that. SOARS was funded through what's called an MRI grant from the National Science Foundation and matching funds from UC San Diego and some philanthropic funding also. Well, I've already spoken a little bit about the ocean-atmosphere boundary. I've shown you here 3 pictures of what happens to that boundary. I'm also including in the middle there the ice-ocean atmosphere boundary, because in polar regions, the ocean meets the ice, and that boundary is also a critical boundary for us that we can also study in SOARS. We couldn't include it in the name, though, because it's SOARS, SOARS. You know, there was no room for ice. We just couldn't put an I in there. We can simulate the ice, but it didn't make it into the name. So why do we care about this boundary? Well, the upper ocean absorbs 1/3 of all anthropogenic carbon dioxide we're busily putting out into the atmosphere. 1/3 of it goes back into the ocean. That's very helpful to us. That boundary is extremely important for air quality in coastal zones. What goes into the water in coastal zones tends to come out again in spray and then comes back on the land. The global oceans, especially in the southern oceans, are very important for making clouds. And clouds can either heat or cool the planet. And as we move forward and we want to understand what the future looks like, what is weather and climate going to be like 20 years from now or 50 years from now, we have to understand clouds. And to understand clouds, we have to understand what comes out of the ocean. And finally, it would be nice to know what sea level is going to be in 20 or 50 years from now. And the ocean interacting with the ice, land-based ice in polar regions, is of grave concern at this time. And that is something that we can also study in SOARS. I'm not going to dwell on this plot, but its purpose is to illustrate something I've already touched on, which is the complex nature of the boundary. There are marine organisms that have evolved to live near the ocean surface over billions of years. They've been competing and living there, learning how to live well. They create unique chemistry that resides near the surface of the ocean and in the ocean. When the wind blows, waves grow and they break, and they create whitecaps. If you've been out to sea on a brisk day on a yacht, you see whitecaps out there. Those whitecaps are bubbles entrained by breaking waves that have floated to the surface and create foam. Well, as that foam disintegrates, it literally ejects bits of the ocean into the atmosphere in a cloud of tiny particles so small that you can't even see them. And what they carry with them is that unique chemistry and biology that lives at that ocean boundary. 1 in a million of those little particles will form ice in the atmosphere at elevated temperature. That ice changes clouds, so the clouds can either heat or cool the planet. What a mess. It's quite the system, and yet that's most of what the planet is. So, how do we as scientists plan to understand the system? We need chemists, we need biologists, we need physical oceanographers, we need engineers. We need all these people to come together and work on this problem. And the first thing we need to do is to train the atmospheric chemists to stop talking in acronyms. Very difficult. CPCs and APSs and oh my goodness. Seriously, language barriers are a thing when scientists come together and they try and communicate with each other. And it's the same with engineers. You talk to an engineer and, as Douglas was saying, well, we want this thing to cost $1 and we want it to survive ocean storms and record for 5 years on a AA battery, and the ship goes out tomorrow. What do you think you can help? You know, it's a tough call. That's why we need engineers. Engineers are the grounding of the scientists who have this vision for what we want to get done, but don't know how to build anything. So the HLab is a place where this kind of collaboration is possible. The HLab was the right place to build SOARS. It is where scientists and engineers come together. Scientists across a broad range of disciplines, but also a broad range of career stages.
I'm not allowed to talk about age. That's forbidden. But I can talk about career stage. So you've got early career, mid-career, late career. They each bring their own advantages and disadvantages. We all must work together across these stages of career to get these problems solved. SOARS was a place, a machine to bring together all these different points of view, all these different takes on the problem. And let me show you a fly-through of SOARS in the HLab. So you can, SOARS there is that blue thing, a wind tunnel on top of a wave channel. You get a sense of how big it is by the people down there. Takes up a lot of the building. Wasn't terribly popular about that in some ways, but we made it fit, and you know, there it is. So there's the machine. We operate SOARS by introducing seawater that we're able to pump in directly from the ocean. Here's how it works. A paddle pushes that water along in a 120-foot-long channel, producing waves up to 3 feet in height. A water temperature handler in the wave channel can heat or cool the seawater anywhere within a range between 33.8 degrees and 86 degrees Fahrenheit. Because the composition of the air is vitally important in creating a controlled environment, we installed an air filter capable of removing all ambient particles 1/3 of a thousandth of an inch from the air we draw in from outside the simulator. We provide the same light that organisms in the ocean would experience through the use of 6 solar tubes positioned just above the channel. A wind turbine can take the air that we purified earlier and blow it through the channel. We can reach wind speeds up to 63 miles an hour, near hurricane force. Finally, just as we can manipulate the temperature of the water, we can also control air temperature. An air temperature handler can produce temperatures ranging from 86 degrees Fahrenheit to -7 degrees. Awesome. You're looking, this video is looking at SOARS through an observation window, 4-inch thick perspex in the operations room. And you can see the waves running from the north to the south. We control the operation of the machine from this room and also can make observations through that port. So here we have it, a storm in the lab with the right biology, the right chemistry, with the winds and the waves. When we operate in polar mode, we can make sea ice. We can pump up carbon dioxide to future levels and see what increases in carbon dioxide do to the water and the biology in the machine. So we can run simulations of the past, present, and future ocean. All right, so SOARS has been in operation for about 18 months, and we have been doing some, what I believe is cutting-edge science in the machine, but I'm not going to talk about that. I'm going to introduce to you 2 of the next generation of leading scientific minds on the planet who have been working in SOARS, who have spent the last 4 to 5 years understanding the machine, collecting data, analyzing data, and understanding how the system works. This is their work, and they will present it to you. We have Keela Kimball. She is a PhD candidate in the Prather Lab. This is what she asked me to read to you, and I'll read this. Keela Kimball is a PhD here at UCSD in the Chemistry and Biochemistry Department, specializing in analytical and atmospheric chemistry. Her research involves using and improving custom-built single-particle mass spectrometers. See, I warned you about the atmospheric chemist. I did. Now, I will explain what that is in a moment.
to study how environmental conditions and anthropogenic influences affect the chemistry of sea spray aerosols. Okay, I'll give you the lowdown on that in just a moment. After graduating, Keela plans to continue studying at the academic or government level with hopes that her research can help change policies to improve the living conditions for us all. So Keela takes these things so small that you can't see them, sucks them into a machine and explodes them with a laser, and takes all the atoms that come out of them and figures out what they are and creates an atomic fingerprint for the composition of these particles. And with this work, she can actually figure out whether you're looking at a little bit of salt or a piece of marine bacteria or some other complex system out of the ocean. It's very exciting work. It's very challenging and very technical, and she's going to tell you how that's been going. I'm also going to tell you about Raymond Liebensberger III. I'm Raymond's co-advisor. I'm wondering if I get to give him some grief. Perhaps not. We do have a thing called the Raymond Protocol in the lab. If anything goes wrong, we blame it on Raymond. We call it the Raymond. Poor Raymond. So, this is what Raymond asked me to read out. Raymond is a PhD candidate working with Dr. Kimberly Prather and myself, and has been at the forefront of SOARS usage. That's very true. He investigates the production mechanisms of sea spray aerosols, the small particles made by breaking waves. So Raymond's figuring out what makes these things, and Keela's figuring out what they are and what they do to clouds, for example. What they didn't tell me to tell you is that Keela is an NSF fellow and a Sloan scholar. And Raymond is he is a San Diego fellowship holder. He won SIO Peer Mentor of the Year and AGU Outstanding Student Presentation Award. So I am thrilled to introduce these two next generation global leaders to you, and they're going to talk to you about their research.
Wow, it's hard to follow that introduction. Thank you, Grant. As he mentioned, I'm a PhD student here at Scripps, and I work with Grant for the past four and a half years, hopefully graduating in the next year or so. I've been working with SOARS since we started working with SOARS, so it's been almost 2 years. So I can't show you everything I've done, but I'll just touch on a little bit of it. So as I had him say, I look at how SOARS generates sea spray aerosols, or SSA. So this video on the left is just showing a slow-mo breaking wave event, and it should hopefully repeat. It's very cool. A deal amount of time that I've spent over the past 2 years has just been sitting in this room watching these waves go by, hoping my instruments are measuring what I hope they are. And so that's what I'm showing here on the right. I won't bore you with all the details, but basically within SOARS, we've looked at different wave fields and different wind speeds, and then all of these different colors are all of the different things that I've measured coming out of SOARS. And I'm hoping to now put all of this into global climate models and improve their estimates based on the cutting edge science that we can do in SOARS. It's very uncertain how sea spray is made, at what size, and as Keela will talk about, what composition. And so the work we're doing will hopefully improve global climate models. We'll find out. And then one of the most uncertain pieces is how temperature affects sea spray aerosol production. And so our latest study, so if you see any errors, don't tell me, this is still hot off the press. But we looked at, as we cool the water from ambience around 23 Celsius down to 2 degrees Celsius, what does sea spray production look like? And so as you can see in this animation, the red colors are warm temperatures, blue colors are then cold temperatures. And so as we cool the water, sea spray production goes up. And that A is not really known, it's not well documented. I'm sure some other people will disagree with these studies, but we've done our due diligence, I promise you, and this is pretty robust. And so we're hoping to then put this into global climate models, because then this means that in a warming climate, sea spray production will go down, and then potentially our anthropogenic influences will have even more of an impact in our climate. that's really all I have to show you. I hope it looks cool. And so next, I will hand it off to my colleague, Keela, and let her tell you all about all of her acronyms and composition.
Hi, I'm Keela, also a senior grad student in the Prather Lab, and will be graduating this upcoming spring, summer. And yes, me and Raymond have had the pleasure of the past 2 years of working with SOARS, and I feel like something neither him nor Grant mentioned is how much work it takes to run that instrument. Me and Raymond have spent a lot of time getting really close to both each other and to the instrument, and have spent numerous hours and days just making sure that it works and praying to God that it doesn't break. And so my part in this, as Grant mentioned, is to look at the chemistry of these particles, because what we know is that aerosols can form clouds, but what we don't know is what aerosols are most dominant in cloud formation, and what's the composition of aerosols that get out at these different wind speeds and at these different temperatures. So there's a lot that's been going on over decades in terms of looking at the physics of these particles and how they're produced. And as you can see with what Raymond showed, there's still a lot of work to be done. So you can imagine how much more work needs to be done in terms of looking at the composition. And so here I'm just showing 3 different scenarios. So what we call low, medium, and high wind speeds, and how the composition changes as a reflection of that. And I know it looks like as we get higher wind speeds that particle counts go down, but the blue line that's shown with the right axis is particle count. So particle counts actually go up as we increase wind speed, but our ability to detect those particles goes down. And so a big part of what I'm doing is, and continuing to do, is improving the instruments that we use to look at these particles so that we can have a better description of what they are and what they're doing. And yeah, I've talked about why that's important. And then here I want to show some data from temperature. So during this past winter, while it was moderately cold outside, we got it really cold in SOARS and in HLab in general. We were all wearing like bubble coats and vests to work every day because we were able to get the channel down to literally 2 degrees Celsius, and blows my mind imagining 36,000 gallons of water at that temperature. And so here I'm showing with the instrument that I use that we also saw the particle counts increase as we decrease the temperatures. And then what's very interesting for me in terms of the composition is that as we decrease temperatures, we start to see this appearance of these larger molecular ions show up. And so just to say that in more plain text, we're getting heavier stuff coming out of the water as we freeze the temperature. And that's important because that means that in places like the Arctic, that we're putting a lot more material out into the atmosphere. And as Raymond mentioned, that with global warming, that means that we may get a decrease of this material into the atmosphere, which will affect cloud formation over the long term. And so, yeah, a lot of this work that we've done and that will be continued to be performed with SOARS, I hope over the next few decades, will just honestly, ideally give us a better picture of what the world looks like right now so that we can better mitigate problems of the future. So that is all.
I certainly sleep better at night knowing that these fine early career scientists are on the job. And thank you so much for your passion, your commitment, for those long, long hours at the machine. And it did break down. We fixed it, but it did break down. So there was that. All right. I think we've arrived at the part of the presentation where Douglas and I are going to answer any questions that you have. And it could be for any of the 4 of us.
First of all, I want to thank you both for a wonderful window into the world that you live in. I think sometimes it's very difficult for people to completely understand
the complexity of the engineering work and the systems that you both study. Thank you so much for that, and thank you for the wonderful talks. We really appreciate you being here. So. I hope that we have some questions about SOARS, SOARS engineering, the HLab engineering. We've got lots of questions. Hang on, I'm going to start here.
Yeah, the very last talk about particle size, aerosolized from wavelength, action, and temperature, I saw a peak around 0.5 micron to 1 micron. Is that known? Are they like biological particles or the microplastics you hear about? Or is that even known?
Microplastics do come out of the ocean, but they don't form a large mass fraction in the kind of global ocean conditions that we're talking about. They're kind of a trace constituent. The particles from breaking waves variation size from 10 nanometers up to hundreds of microns or millimeters even, depending on ocean conditions. So does that answer your question? It does. Okay.
May I ask the two of you to speak in the microphone so we can catch that?
You're working with 36,000 gallons of water, and you're temperature controlling. You're also working with the biology in that. How frequently do you change the water?
Yeah, good question. So there are a lot of things we can do with the water. We can fill it with fresh water or salt water. If we put fresh water in, we can keep the fresh water going for, weeks or months if we want. And we don't want to waste water. So right now, SOARS has fresh water in it, and we can keep that water running for a long time. We've had a lot of tours recently, so we put fresh water in it. With salt water, it depends on what we want to do. We have UV sterilization filters, mesh filters, and a sand filter. So we have a variety of controls. We can rip out very small organisms or just leave the tiny ones there, the viruses and the bacteria, and rip out the larger organisms. Or we can sterilize the water if we want with the UV filters. If we sterilize it, well, we can keep it around for a lot longer. When we're growing blooms, we have light pipes that bring light in, and we have 40,000 watts of PAR LEDs to grow organisms. Even that turned out to be not quite enough. We can stabilize a bloom, but we can't get the bloom to really peak. That has to be done outdoors, so we're looking into what we can do to improve that. But a bloom will last from, say, 10 to 14 days, and it grows, it peaks, and then it decays. And as it's decaying, the water, the bacteria and the viruses take over. Well, not something that we particularly enjoy. So at the end of a bloom, then we'll let the water out. We have a sewer permit, and the water release is carefully monitored, logged, and controlled. So we are allowed to do it, but we try and conserve water as we can, and we use it as responsibly as we can to get the science done. Does that answer your question? Okay, great.
With the tragedies of Hurricanes Helene and Milton sort of on our minds, in the media they always talk about the sea surface temperature supercharging the storms. I'm just wondering if you or your grad students have any information on how the particles coming out, and particularly as those might change with our changing climate, how that might influence hurricanes, or is it still too early to say?
Take this one. Okay. Yeah, great question. The experiments that have been run in SOARS to date have focused on droplets that come out of the ocean that are less than, say, 1/100th of a millimeter in scale, less than 10 microns. The droplets that you're referring to for hurricane formation are significantly larger than that. And SOARS could be used to study those droplets, but we haven't. However, what we have done is form a collaboration with some investigators on the East Coast at Florida International University.
And the civil engineers there want to build a huge hurricane simulator. They have something they call the wall of fans, and it's like gargantuan. They have this big building that has a wall of fans in it. And they have this very dramatic demonstration where they have a building in the building. And they turn all the fans on. And the building, it gets to a certain wind speed, and then something gives. Some little piece of that building gives up. And then it just explodes into a cloud of debris blown by the wind. Then they do the whole thing again with $25 worth of engineering upgrades. And the building stands. It survives the winds. It's very, very dramatic. When I saw that, I was inspired because I think we're public servants. We spend all this money. We need to return value. And what better value can you have than trying to help build hurricane-resistant infrastructure where we can engineer and build buildings that will survive these extreme weather events. So they came to SOARS, and they want to build this half-mile long hurricane simulator that would go up to Category 4, Category 5. It's like a $200 to $300 million thing. I think it's a fantastic idea. I really, I want to be part of it. I want to go out there. I want to see the whole thing. But the problem is we don't know how to build it. We don't have the engineering data to understand the effect of the winds and the waves to build such a thing. So they came to SOARS and they said, your fans are too small. We will put in bigger fans. And they did. And so we went from almost Category 1 up to well into Category 2 wind speeds now. We can get up to 145 mile per hour winds in SOARS. And they ran experiments to get the engineering data to take back to the National Science Foundation to support their proposal to build this simulator. So that's what we have done for hurricanes so far. I hope that answers the question.
So I'm over here. I understand that SOARS can be available for lots of people around, or organizations around the country, if not around the world. So a lot of people want to use it. How do you decide the priority of who gets to use it?
Would you like to book it? Great question. We have SOARS is what's called a recharge facility. It's available to everyone. If you're a UC user, you pay $1,800 a day. If you're academic, external to UC, it's $2,400 a day. And if you own a company, it's $6,000 a day. So commercial use is a little bit more expensive. At the moment, we've not had to make the tough decisions about who's going to use it and who's not. The use has been, it's been used probably about 50 to 60% of the time it's been on since it was commissioned. But it's only been a small number of groups, and we've just been able to resolve things locally. I imagine in the near future we have a lot of people coming and asking about it, want to do all different kinds of research, waves and corals, wind speed effects for planes, polar study and international polar studies coming in. Then we have a scientific board of advisors. It's the gang of 5 that I said at the beginning, who are the PIs. And then we will prioritize the work according to what the science is, who the investigators are. We'd like to give priority to younger investigators, for example, and so on. So we have a series of operating procedures and policies in place, and an advisory board to make those decisions. Does that answer your question? Great, okay.
And the question back here.
Hi, based on tonight's presentation, I've been trying to develop my own personal high-level understanding of what the relationship between SOARS the machine is and SOARS the program is. And I think I can do it in 25 words or less. And you tell me what parts I got right, what parts I got wrong. So the machine, as simulators go, is resolutely analog. That is an analog simulator. So I'm assuming that the long-term goal of the SOARS program is to study the phenomena the data that comes out of the analog simulator with the goal of using that data to ultimately develop digital simulations of the same phenomena, and that those digital simulations will become part of what was mentioned at one point as a global climate model, which I also assume is a digital simulation. How much did I get right here?
I'm very excited that you asked that question because I wanted to talk about this and Dale told me I couldn't. But now I can talk about it. This is absolutely fantastic. Thank you so much. So this is actually a really fascinating question. It's why don't we just simulate everything? We've got computers. Let's just do that. And in fact, global climate models are algorithms that simulate the planet on silicon. Great, fantastic. What's the problem? They're wrong. Well, I can't say they're wrong. I can say they're challenged. Yes, there are challenges with them. But we can't simulate everything. I actually did this calculation one day, and I was like, okay, what would it take? There's a range of length scales that you need to simulate over, from the smallest scales to the largest scale. And that determines the amount of memory you need in your computer, because you set the whole simulation up like a grid, like a chessboard, but in 3 dimensions. And the smaller the scale, the more grid points you have, right? Okay, so the largest scale is what? The scale of the planet. Oh, that's fairly clear. What's the smallest scale? Well, it turns out the smallest scale is about 10 nanometers. That is, a nanometer is 1/1000th of a meter. It's not much, right? And so when you scale that up to planetary scales, and then how many of you have heard of something called Moore's Law? Moore's Law. Yeah, some people have heard of Moore's Law. Moore's Law is this very famous and very interesting law that tells us that the amount of computer chips you can get on a computer sort of doubles roughly, I think it's roughly every 4 years, although I might be getting that wrong. But it keeps on every 2 years. It keeps on doubling. It doubles and doubles and doubles and doubles. So it's exponential. I figured out if you took all the memory on the planet today and you applied Moore's Law, how long would it take before you could simulate the whole planet? It's significantly older than the age of the universe. You just can't get there from there. We cannot get out of this business of thinking about the problem. We can't just hand the problem over to a computer. We have to continue to understand how the system works. And SOARS is a tool to stimulate our imagination, to stimulate our hypotheses, to help us understand how this complex system works. We can't just turn SOARS on and let it run either and just like, okay, well, there it goes. Yeah, great. Okay, what does it mean? How do we then take the output from that and give it to the people who run the computer simulations so that they know they're getting the right answers? And yeah, SOARS is this great analog simulator built in response to the fact that we can't simulate everything with computers. Even if we could, we wouldn't know what to put into the computer. We wouldn't get the initial conditions right. We still are in that business. But that is an insightful observation about what we're doing. And we are building an analog simulator to meet digital simulation and bridging that gap. Thank you. I really wanted to talk about that.
I'd also add that in my present position with the Center for Western Weather and Water Extremes, one of the things we do is launch weather balloons during storms to study atmospheric rivers. And those data are fed right back into the global climate models, or the global weather models, not climate, but global weather models, because they're continually trying to improve the process. And it's only through that data that we collect from in situ sensors, whether it be radiosondes, weather balloons, or some of the other things that we deploy in weather stations around the West, that they can improve on that technique. And so they love getting our radiosonde data, our weather balloon data, because they get that in real time and they can say, hey, we did a good job today. Or tomorrow, oh, we got to tweak this a little bit. So it is a process. It's a process between how you make a model better, because models are getting better and they're getting, have the capability to do better things. But we also need to make sure that, is that answer correct? Does it validate what we're seeing in the real world? So, my point. Thank you.
Last question.
Grant and the entire team, research team at SOARS, you guys, thank you for being here and giving this presentation. I'll ask a question that's not meant to provoke, it's just meant to ask some more information. Oftentimes research doesn't lead to action or a solution-oriented action. It just follows more research and more understanding. I heard a report that with the warming of the planet, polar ice caps are melting and it's releasing methane into the planet, which is heating up the planet at an exponential rate, compounding the effect essentially. In some of your futuring work, are you studying this effect on sea ice or polar ice to understand what that impact is having on a warming planet? And are you offering solutions to companies or organizations that are action-oriented?
We are not studying the release of methane from the warming Arctic tundra because, you know, it's an ocean simulator, which is not to discount the impact of methane. The lifetime of methane in the atmosphere and the lifetime of carbon dioxide is very different. Methane is a more potent greenhouse gas, but its lifetime is shorter. It's a very important issue. The stability of the clethrets along the seafloor is also of grave concern. If they there's a lot of methane locked up in clethret form on the ocean's margins, and if that destabilizes, that will only accelerate and exacerbate the situation. In my life as a professional scientist, I do not actively work on geoengineering or mitigation strategies or policy, although Keela is interested in working on policy. I work on a fundamental understanding of the system. In my private life, I work with a company that is working on carbon capture. And I do pro bono work for that company, a mixture of consulting and pro bono work, because I believe I can help recapture some of that carbon dioxide. That is my private life. I keep it distinct from the university, but I work on that, you know, I think about that every day. And the reason that I'm very excited about that is I don't think academia can come up with working, you know, unless you believe in a Deus Ex Machina kind of solution. One day somebody invents a new widget that solves all our problems. I'm not saying it couldn't happen. It hasn't so far. Didn't happen today, and tomorrow doesn't look that good, you know. So, you know, who are the people who are going to make these kinds of changes real? How can we sell to billions of people that we must give up the comforts of life because we've got to change the way we use energy? How do you make that argument? Well, you make it by going to companies that will make it commercially viable. And those people, the industrialists, they know how to make things that people want to buy, that fits within our economy, that works within our culture. I'm working with those people who can generate solutions that will be sustainable and scalable because they will be economically viable within our current economy, which means, you know, we're not asking people to make sacrifices. In some cases, you know, it could be good engineering, good value for money. So that's what I do in my private life because I really do care about these issues. And it makes me better waking up in the morning knowing I'm working on carbon capture. Yeah, so there are two parts to your question. You're welcome.
Well, let's thank both of our speakers. And Keela and Raymond, thank you so much for giving us a glimpse into the future. We really are grateful for you participating. And I think this was a wonderful journey from the past history of the HLab to our future generation of scientists. So really appreciate you sharing it with us. Hope you'll come back on November 18th next month for another great lecture in the Perspective series. And we hope to see you then. Thanks for coming.
Got the job done.
As usual, our speakers will be around for a little while to answer a few more questions if you have them.
Thank you for having us. I appreciate it.
I think that turned out really well. That's great. Go ahead, please.
There's special ribbons that they use.
Take on most of my retirement. There's one last little bit from GA, and then next year I have to, by law, I have to start making money out of my 401k and 403b. It's not a lot of money. There might be different studies done by different people. I don't remember
Not a problem with everybody, but they contact me and I'll make sure that it goes on the whole site. I really, I'll see if I can do that.
From some cause and effect known back then. Yeah, I know it. That correlation wasn't. Somebody got a 10% brain cancer than blood cancer.
I don't know anything about it. I did hear this thing out on the
One of the programs in research in 20 years of service, part of my campus.
think the physician